In the previous section, 7.1, what we did was find the area that was bounded in a region between two curves. And that was as simple as just subtracting the area underneath the curve that appears above the other one, taking that area from the top curve, that top function, and then subtracting the area below the sort of lower function. Um, and like once you figure out more or less what that integral is supposed to look like, which function's being subtracted from the other, the integration's pretty much simple because, all the stuff from module one really was a crash course in all your integration techniques that are used to do these kinds of things. Okay. So section 7.2 gets into this thing called the disk method, which I think we sort of need to draw some pictures so that we can get an idea of how to handle these kinds of problems. So for a simple example, just imagine that we have some axis like the x-axis, and we just draw a rectangle that's sitting on top of the x-axis. Let's see if I can make this a little bit. There we go. Straighten it out. So that rectangle is just sitting on top of the x-axis, and it has some area here. Maybe I'll go ahead and shade that in, right? Some area. And you know from your basic geometry from grade school that area is just going to be the length times the width. In this case, the way the textbook codes those variables, length and width, is it refers to the sort of height or the length of the rectangle as the radius, as we're thinking about sort of a circle extending from the center at the x-axis all the way to the top of that rectangle. And then the width is just W, so that's really nice. So whenever we say the height of the rectangle, we're going to be using R to indicate its radius or height. Okay. Now imagine that we took that rectangle and we rotated it around the x-axis. Kind of weird to have this like 2D image, but you kind of have to think about we're circling in a 3D space around the x-axis here. What you would end up getting is a shape that kind of looks like a wheel, right? Or a disc. If you've seen a wheel of cheese at HEB or something like that, that's the shape that we would get if we rotate this in that three-dimensional space around the x-axis. Okay, so by before performing this action of revolution, okay, that's the way it's described in the book, anchored to the x-axis, we obtain this circular cylinder or this disc. Okay, and so if you just think about how do we find the sort of area of this circular face of the cylinder? Well, that would just be pi r squared, right? Pi r squared would represent the area of that circular face. And then if we want to think about the thickness or the length of the cylinder, then we would just multiply it by whatever that distance is, or that width, or that thickness. So we can think about getting the entire volume for this disk or for this wheel by just taking pi r squared, that's the area of the circular face, and then just multiplying it by how thick is that cylinder or that disk. Okay. Does that seem like a simple idea? Right. Again, and I think like back in maybe middle school, high school, when you guys took geometry, you probably calculated the volume of a cylinder just by doing this very thing, finding the area of the circular part and then just multiplying it by the height or the length of the cylinder. Okay. But now we're in calculus and we want to think about this as not just these simple cylinders, but some maybe a little bit more complicated of a shape that is cylindrical in nature. Okay, so what we want to do is like keep this simplified analogy in mind when we're finding what's called the region of a plane that's revolved about a line or an axis of revolution, because that's going to result in what we call a solid of revolution. Okay. But again, as a simple analogy, I want you to think about these cylinders that we're creating. Okay. So to find the volume of a solid of revolution, you can use one of the formulas below, depending on which variable are you integrating with respect to. Okay. So like for this volume formula, this looks complicated, right? But essentially it's just pi r squared, right? And pi r squared would be like um, the area of a circle. But since we're integrating with respect to x in this, that would be like we are revolving it around a horizontal axis. So think about like revolving that around the x-axis, for instance, where the dx is kind of playing the role of the width of the cylinder. Okay. But if we were revolving something around a vertical axis, think like the y-axis is going up and down, then we might want to integrate with respect to the y variable. But still, we need to sort of visualize what is the circular part that we're trying to find the area for, and then multiply that by the thickness or the width of the cylinder. So this dy is still going to be the width of the cylinder, but we really want to have a well-drawn picture in order to get a grasp on what does this shape look like? Because they're not going to be perfect cylinders. If they were cylinders every single time, then we could just use the cylinder formula to do that, okay? All right. So that's kind of like the overview of what we're going to be looking at today. So let's look at some examples now. Okay. So the first example that is presented in the textbook says, find the volume of the solid formed by revolving this function, f of x equals the square root of sine x, about the x-axis from 0 to pi. So I think that the number one key that you're going to find for these, number one thing is that you need to draw a sketch of the function on this interval. So on the interval given. You might want to do so with pencil, because if you do make a mistake with pen, then it's going to be a lot of scratching out, right? And you won't be able to erase unless you're using erasable pen. So I am also going to do that just to make sure. Well, I don't have a pencil on me, so we're just going to let go and let God today. Okay. So let's think about what this function looks like. First, let's go ahead and I'm just going to draw the x-axis. Okay. There's my x-axis. I don't really care where 0 is, but I'll just put it here. 0 is here, and the interval is stretching from 0 to pi, so I'm just going to say pi is going to be the other end of this function. Okay. Now, we want to think about our function values as being y values. So you might want to extend this little region here and call this the y-axis. Okay. But we really want to find what the endpoints of this function are, just like we did in the previous section. So to find those endpoints, all we need to do is plug these x values into the function that we've been given. Okay. So let's do that. The first endpoint is going to be f of 0, which is the square root of sine of 0. Which, can anybody tell me off the top of your head, do you know what sine of 0 is? Yeah, I'm pretty terrible at remembering these things as well, but I think it should be 1, right? Because 1 would be the y value. At 0, the y value is 1. Okay. So, I mean, you could take the square root of that, but it's just going to be 1 anyway. So we'll leave that as it is. And then um, we will want to, let's see, where are we? Oh, then find the other endpoint, which is f of pi, which looks like what? The square root of sine of pi. And what is sine of pi? Sine of pi, the y value would be, are you sure the sine of 0 is 1? Just gonna double check that in the calculator. It's 0, guys. Okay, so this one should have been 0. That's why we don't want to use pen. This one also, I think, is going to be 0. Just going to do that sign of pi in the calculator just to put that in. Okay, 0. Okay. So those are our two endpoints, and that doesn't really give us a good idea of what's going on in the middle of the function since those y values ended up being 0, right? So what we could do to get a better image here is just plug in some point in the middle, like pi over 2, right in the center, just to find the middle point, and sine of pi over 2 just to get that extra point here would be, well, it's the square root of sine of pi over 2. This one should be 1. Okay. So maybe we just need to go back and review our unit circle a little bit. It's early on a Monday morning, so like I'm gonna give you guys the pass on that one because I was just trusting you guys as well because I'm kind of tired myself. So that's gonna be 1 up here. So we're gonna have a point there. Okay. Well, if you don't want to find a bunch of different points to find exactly what this graph looks like, I think we can all sort of say it's going to be kind of like this, maybe like a parabolic, a little bit upside down parabola. But like we said, we can go ahead and throw that in the calculator to get like just a better idea of what that function should look like. So we'll just put the square root of sine of x into the calculator. And then we just want to sort of look at that region between 0 and pi. So we'll go to the window here and change our x values here from, well, it looks like it only goes up to 1. So I'm just going to go up to maybe -2 to +2. No, those are x values, my bad. So I'm going to go from 0 to pi. We can put pi in here. And then the y values don't go all the way up to -10 and or down to -10 and up to +10. So we're going to make those like, I don't know, we could do 2, -2 to 2. And we can say this kind of like upside down parabola type shape. So our graph, or at least the one I'm drawing here, is not going to look perfect, right? Theirs is a little bit squished, kind of like a flattened football, a little bit, just that side of a football. But remember, a picture is just a model that we can play around with to get an idea of what shape we need to get. Okay, so does anybody have any questions about how to graph these shapes? Because that's going to be the most important, one of the most important steps. You guys okay with that? Anybody in Zoom have any questions about graphing that? Okay, and maybe I'll write over here that these notes are just like graphing those points by hand. But as you notice, like I'm always going to do a little bit by hand and then say, okay, well, if I have a graphing calculator, I'll let the graphing calculator kind of help make my picture a little bit better. Okay. Now, here's going to be the next hard part, which is, and maybe I'll put number 2 here for the next step. We want to visualize what's sometimes called the representative rectangle. And revolve it around the given axis. Okay. So this idea of a representative rectangle just goes back to when we introduced Riemann sums and finding the area of a rectangle, right? That's how kind of we defined the integral. Well, if we just chose like an arbitrary point on this function, right? So I'm just going to choose this point here. Just randomly choosing this point, we could have chosen any point along this curve. We could say like that's the height of some rectangle. here. And I'm just kind of exaggerating how large that rectangle is. And the idea is that we want to sort of figure out, well, what's going to be the radius of this rectangle, right? Because what we're going to do is revolve that around the x-axis. And so remember, when we talk about the radius of this rectangle, we're really talking about its height. So the height of this rectangle we can label as r of x because it's going to be some function. And then the thickness or the width of this rectangle, you can kind of see this rectangle width is measured in the, well, from left to right is how we drew that width. So really that's the thickness or the width of the rectangle that we call dx. Okay. And it's dx because we're going from left to right. We're going in the x direction there. Okay. So we have to recognize that this rectangle, the height of it at any given point on this curve is going to be whatever the height of the function is. So r of x is just going to be the function that we're using in this case, right? So that's going to be the pi, I'm sorry, the sine, square root of sine of x, okay? That's going to be the radius. And then the height, sorry, the thickness, w, is equal to our dx, right? And that's the thickness of what are going to be these disks that we're building. Okay. And this drawing is getting a little bit busy, so I'm just going to kind of do another one down here, just a really brief sketch. We already kind of know what this shape looks like. So I'm going to draw this kind of flattened football shape that's probably more like what you guys are seeing. And then what we're really doing is saying, okay, so there's some rectangle somewhere for that shape, and we're just rotating it such that now we're kind of getting another rectangle below, and we're getting kind of this circular shape here, right? So we get this kind of wheel of cheese or this disc. And that is going to sort of permeate through the entirety of the area of this function, such that we're kind of getting this football shaped thing. Okay. Visualizing things in 3 dimensions can be kind of tough. Okay, but this is the volume that we need to calculate. Does anybody have any questions up to this point? Okay, I will maybe zoom in a little bit more just so you guys can see that shape. And I don't know if it helps to make this now like a solid, this is kind of like a slice of that overall shape that we're going to be sort of tracing out with this integral, right? But this is the disk that we're talking about. And it has that radius here. You can measure the radius in any direction, but there's our radius, and then there's the thickness dx. Okay. So now we kind of know where we're going, and the third step is going to be to set up our integral. We know what our radius is. We know the thickness is going to be represented by dx in our integral, and now we'll put our integral together. You guys ready for that? Okay, let's see. So step 3 is going to be set up the integral. which is v is equal to pi from, I'm going to say a to b. I'm just setting up the formula again. And then it was just, um, in this case, just the radius squared. So r of x dx. Okay. Okay, so then that means that this is just pi. We went from 0 to pi here. Those are limits of integration. The radius was the function, the square root of sine x, and then we have dx here. Okay. That's going to be pi going from 0 to pi. So pi times the integral of, and then we really hate using roots whenever we're taking integrals, right? We always want to convert those to powers. So this will be a lot better looking if we do sine of x to the 1/2 power dx. And then we can do a simple substitution there, right? Um, that's just going to be u equals sine of x. Du is going to be equal to what? So the derivative of sine should just be cosine. Dx. But we don't have a cosine in our function. So how are we going to approach this? Oh, there it is. I forgot about this square, right? We're squaring this. And so the square times this 1/2, that's going to help us right there, right? Because when you have a power raised to another power, those powers multiply. So 1/2 times 2 just becomes 1. So this is going to be pi times 0 to pi integral of just sine. So again, a little slow to put everything together this morning. We did not need the substitution at all because the volume formula here has this squared, so we were able to cancel out that square root there. Otherwise, this would have been a more complicated integral, but we can take that. That integral is just going to be negative cosine, right? So remember that if we have d dx, a derivative of cosine of x, is equal to negative sine. Then if we sort of think about this as a differential equation and sort of integrate both sides, just going to put over here, this is just scratch work. Then that means we would have cosine of x is equal to the negative integral of sine x. And we can simply divide both sides of this by -1. So we can get that the negative cosine of x is equal to the integral of sine x dx. So this guy is just going to be pi times that negative cosine of x. And then we evaluate from 0 to pi. So that's just going to be pi, maybe we call it negative pi cosine of pi, and then minus, then we would have a negative pi cosine of 0 when we evaluate that. So now we just need to think about what is the value of cosine when the angle given is pi. And so if we're sort of on, this is kind of me in my head visualizing the unit circle, right? This is pi over 2. This is 0. This is pi. If we're over here, cosine represents the x value, right? So the x value of this point would be -1. So this is just negative pi times -1, which would just be pi minus, um, or since you can think about this like negative negative, so that's going to be a plus um, pi cosine of 0. And so if we're over at this point here, the cosine is going to be +1. It's going to be plus pi times 1, which is just pi. Okay, maybe I'll put that in here, pi times 1. So pi plus pi in the end is just 2 pi. We'll go ahead and label this as my unit circle, my mental unit circle, just the upper part of it. Okay, and that's how I was evaluating these parts here. Okay. Questions, comments about that example, right? This is what represents that volume of that football shape that we found. Right? Any questions out there? Yeah, I'm sure that maybe I threw you guys off when I was started going in on a U substitution over here. And like those mistakes are going to happen from time to time. I always tell students that like I'm a human being and it's really difficult for any person to do multiple things at once, and me talking and delivering this material to you guys and working through the problem and commentating the entire time. Sometimes I get turned around, so like it's not a big deal if you jump in there and think to yourself, oh, we need to sort of do a U substitution, but then you back up and say, hey, that's not going to work out. Just like I did there, I think it's a learning moment, right, for any one of us that, like, if you try to do a U substitution like I did here, you notice that I immediately slowed down and was like, oh, well, if I tried a U substitution, then I would be looking to cancel out like a cosine x dx, and there simply wasn't that in the formula, right? Or in the integral that we were working with. So like clearly that wasn't the right strategy to take. And so then that's when you start looking for, well, what did I forget here? And I definitely forgot that the area of the circular region that we were doing is like radius squared. So that square needed to be a part of that example. And that helped us sort of clean this up, right? Once you fix that mistake, then the problem should start flowing really nice and neatly. But like that is an intuition that you start developing as you go through more of and more of these problems, where you starting to feel like, okay, if things are moving smoothly, then you're on the right track, that you're understanding what's going on, and you can kind of trust the process to lead you in the right direction. But if you're starting to get those friction points or like those points of turbulence in your brain, you're like, hold on, this seems wrong, then that you got to start to learn to trust your gut and say like, okay, maybe this is wrong. But it takes a little bit of practice before you can start doing that and build the confidence to say, all right, let's just start over, right? And luckily we didn't have to do that here. Okay, any questions before we move on to the next example? Does this feel like a lot? Any comments out there in La La Land, whether in person or in Zoom? Yeah, what's up?
How did you get that volume?
How did I get the volume formula?
Yeah.
Okay, yeah. So that was just something that was given to us. Just based on our recap, what we're doing is kind of trying to find the volume of these washers, these circular discs. Sorry, not washers, these circular discs. Washers have holes in them. And we thought about it like just finding the volume of a cylinder. And the volume of a cylinder is just going to be pi r squared, and that comes from the area of the circular face times the width, whatever that little width is. So like whenever we start drawing these functions, we're going to be sort of thinking about this analogy of what are these cylindrical shapes, right? And so that's really the integral that we were applying, right? The integral formula for these volumes are going to be pi r squared times the width of that cylinder, right? So we're just integrating with respect because we're really trying to, find this entire area here under the curve, but we're using the pi r squared part, and it sort of rotates that curve around the x-axis so that you get this full shape here, right? And so that's where that washer or that disk is coming from. Okay. So that's why I was able to pull out that formula pi r squared dx. Okay. And in some textbooks, they put the pi on the inside of the integral, but since we know that's a constant, we can just pull it out of the integral. So you'll always see me write it on the outside of the integral. Okay. Let's do another example just so we can get, some more practice looking at these functions and kind of drawing what is the shape that we're examining and how are we rotating it? Because it's going to take a little bit of art now, right? You have to draw these pictures clearly so that they make sense in your brain, right? And if you're not like coming from an art background, which I actually did when I was in high school, did a lot of visual arts. So it was easier for me to sort of visualize these shapes in 3D space, but I know that that can take some practice. Okay. So example 2 says using a line that is not the coordinate axis. Okay, so we're going to be revolving around something that is not the x-axis here. Find the volume of the solid formed by revolving the region bounded by the function 2 minus x squared and g of x equals 1 about the line y equals 1. Okay. So we want to think about this a little bit by drawing it out. So we're going to do those set of steps again. Let's go ahead and draw the function. And I think that it's a really good exercise to draw a lot of these by hand so that you can get used to it. Okay. Does anybody need a little bit of time to write this down? I don't know if this was on the printed version of the notes I gave to some of y'all. Okay, I'll give you a little bit of time to write this down. Okay, so we want to draw these functions, and we have two functions this time. We have f of x is equal to this thing. Just by examining the equation here, I have a negative x squared, so I know that that's going to be an upside down parabola. It gets really useful to identify when you're dealing with a quadratic function, right? To be able to visualize that. G of x is a constant function. And constant functions just represent these horizontal lines at a particular y value. Okay. And we want to revolve around the line y equals 1, which happens to be the exact same function as this. So let's just go ahead and draw these functions sort of floating in space. So I'm going to draw a little y-axis here. Maybe I'm going to put my x-axis here. And the first thing that we might draw is kind of the lower function. G of x is equal to this straight line here, which is at y equals 1. So this is y equals 1. And so I'm going to draw a horizontal line here to represent g of x, okay, equals 1. So the axis is the same thing as this function here. Okay, I'm going to put same as g of x. Okay. And then where the parabola here intersects, well, you can think of this like the parabola we have a positive 2 here, so that means it was pushed up twice, right? 2 units in the upward direction, and then is just like an upside down parabola. So if you want to find the endpoints, just to be consistent, we can find those endpoints for this function. So if we wanted to find f of 0, that's just going to be 2 minus 0 squared, which is just 2. So like up here, That's going to be at 1 point. And then we might want to find where this intersects, where these two functions intersect, right? So the intersection of two functions you can always find by setting those two functions equal to each other. So that would be like 2 minus x squared is equal to the other function's just a 1. Okay, so this should be a fairly simple quadratic equation to solve. I'm going to, what do I want to do here? So, well, we can go ahead and there's a couple of ways you could do this. I'm just going to subtract the 2 over to the other side. Okay, so I get negative x squared equals, this will be negative 1. You guys okay with that? Okay, sorry. Then we're going to divide by negative 1, so we get x squared equals 1, and then just taking the square root of both sides to cancel out that square, we get x is equal to plus or minus 1. However, for this shape, we really just want to get the positive 1 over here. So like this x value over here, we can call 1, and it intersects here at the y value of 1. Okay. I mean, you could plug that positive 1 into the function, either one of them, but you would get 2 minus 1, which is going to be 1. I hope that was kind of an easy calculation to make. So that point right there is 1 comma 1. And then our upside down parabola looks something like this. Okay. Um, Actually, this shape is not just going to be over here on the positive side of the x-axis, but as we saw, we have two x values of interest, and that's positive and negative 1. So if I plug negative 1 into this function, I have to push my drawing out a little bit here so that I can go out to negative 1. And if I were to plug a negative 1 into that parabola, then I would also be hitting the other side of this constant function right here at negative 1 comma 1. So we have a similar sort of football shape here, but it's floating above the x-axis. Like this is the region here that we're trying to rotate, right? Any questions or comments? So I'm just going to make a note here that we had two x values. So that means that we had two intersections for these functions, right? So that's why I had to find these 2 points over here. So if you think about revolving this shape around this axis, we're not revolving around the x-axis. We're revolving around the axis y equals 1. Then we would get a shape that kind of looks like, I don't know if I'm dating myself. Maybe you guys are too young for this, but it kind of looks like Hey Arnold's head, right? It's a football shape, just like the last one. Okay. So when we revolve this shape around, what we're going to end up getting is something that looks like this. There's the original shape. We can draw sort of a representative rectangle here. Down here, we have the axis that we're revolving around. This is y equals 1. And if we were to rotate this, we would get something that looks like this sort of like this, sort of like this, right? There's our kind of, again, they call it the disk method because we're getting these little disks. But, you know, as I draw it, it kind of reminds me, especially since I'm using red, it reminds me of those little Baby Bell cheeses. So it's like a tiny little wheel of cheese. Okay. And that is going to help us kind of flesh out the whole region around this shape. Okay, so that's our 3D solid. And so we need to ask ourselves, how do we find the radius? So the radius goes from here to the edge of our function. This part up here, trying to make it a little bit thicker, is determined, the top edge of that shape is determined by the function f of x equals 2 minus x squared. But the radius doesn't go all the way down to the x-axis. It just goes to y equals 1, which was the function g of x. Okay. So here, our radius is really going to be the distance. So r, this distance, is determined by the top function minus the bottom function, or the lower function. And that's how we're finding the distance between them. I'm going to put between as b/w. Okay. So that's going to be 2 minus x squared minus the function below was just 1. Okay, so that's going to be our radius, and we can simplify this. Didn't need the brackets here necessarily, but we're just going to combine like terms, right? So we could drop the brackets and say, okay, 2 minus 1 is just going to be 1. When we combine like terms here and here, and it's still going to be minus x squared. Okay, so that's going to represent the radius of this volume. Any questions, comments about figuring out that radius? Okay, well now it's time to sort of set up our integral so that we can calculate the volume, right? So bringing in our volume formula again, the volume is going to be equal to pi times the integral from a to b of this radius function that we found, r of x squared dx. Okay. So let's plug in what we determined to be the radius, and we'll look at our picture to see what those limits of integration are. So we have pi times, the limits of integration are, and I'm going to sort of pose this to you guys, from what x value to what x value to get the full shape. And look at the drawing that you made. What are the x values that represent the endpoints of this shape that we're trying to sort of find the volume of? I see some answers in the chat. Okay. And that's exactly right. So if you look at the shape extends from -1 all the way to 1. So like if we're integrating with respect to x, then you want to say what's the farthest x value here? That's going to be a. And we're integrating all the way to the value b here. So these are your limits of integration. Okay. And that's why it's important to have this entire shape kind of drawn out and sort of plotted on the x and y coordinate axis so that we can kind of measure how far are we taking this integral, right? So we'll go back here and we said we're going to integrate from -1 to 1. We also found this radius function, which was this modification that we made by taking the distance between the top and the bottom function, just subtracting the top, taking the top function and subtracting the bottom function. So I'm going to put this 1 minus x squared into the brackets here. 1 minus x squared. And then don't forget that this is radius squared, so this function is going to be squared before we take that integral. Okay. Now, I've been thinking long and hard about this class and just recognizing this is not a value judgment. This is just an observation that sometimes when we're learning this calculus stuff, the calculus tends to be the easy part of the problem, and then we tend to make a lot of mistakes when it comes to like the algebra. So like let's just tread carefully when we're going through a problem like this. I always like to do my scratch work off to the side just so that I don't confuse myself. If I'm going to square this expression in the brackets, a lot of times students will make the mistake of just squaring the 1 and squaring the x squared, but that's not how you square a polynomial. What we have to do is tell ourselves, well, if I have 1 minus x squared and then I square that, that's equal to 1 minus x squared times 1 minus x squared. So we actually have to write it down completely and then FOIL it out. Again, this might seem like a college algebra level stuff, basic stuff to some of you, but I just want to make sure that I say it because sometimes we do, in sort of our haste, trying to quickly get through these problems, we will make these little mistakes. So let's not cut corners here. Let's go ahead and do this foiling. So this is going to be 1 times 1, which gives you 1. 1 times x, negative x squared is going to be a negative x squared. Negative x squared times 1 is going to be a negative x squared. And then negative times negative is going to be a positive, so we're going to get a positive x to the 4th power. Combining like terms, we get 1 minus 2x squared because we have 2 of these negative x squares, plus x to the 4th. And then just for, at the very least, my OCD reasons, I'm going to go ahead and put that in the correct order, right? Not correct with a capital C, but correct with lowercase c. Because it doesn't really matter that we put this in order. What really matters is that we FOILed that out correctly and now have the polynomial that we're going to integrate, because that's your r squared. Okay. So I'm going to replace this now with this scratch work that we've done over here. So let's go ahead and rewrite this integral. Pi from integrating from -1 to 1. And then the integral that we're actually taking is x to the 4th minus 2x squared plus 1. And then all of that dx. Okay, which means that we can integrate each of these terms separately. Okay, so we'll have pi times, this will be 1/5 x to the 5th power. Then this will be minus 2/3 x to the 3rd power plus x. And then we can evaluate this bad boy from -1 to 1. Any questions about the integration process? That felt like the easiest part of this problem, right? Okay. So now we can evaluate this. Equals pi times, and then we're going to plug positive 1 into all of these. So 1/5 times 1 to the 5th minus 2/3 times 1 to the 3rd plus 1 minus pi times 1/5 -1 to the 5th power minus 2/3 -1 to the 3rd power plus -1. So again, at that point, if you're feeling like, okay, I'm exhausted at this point, you can throw that in the calculator, but I'm just going to do a little bit more processing here. So this is just going to be pi times, this is going to be 1/5 minus 2/3 plus 1 minus pi times, -1 to the fifth power should stay negative because we have an odd exponent there. So that's going to be -1/5. Same thing here. This is going to be a -1 since we're raising that to an odd power. So if that's going to be a -1, then this is going to change to a positive 2/3. And then that's going to be a -1 there. Okay. Now I'm feeling exhausted. Going to go ahead and throw this in the calculator. Okay. Or not. I don't know. Let's go ahead and see what we can do. Both of these have a pi, so I'm going to factor out a pi. So that's just going to be 1/5 minus 2/3 plus 1. Factor out a pi, so this is just going to be, um, let's see, what will it be? Yeah, it's already a dicey situation. That's going to be a positive 1/5 when I distribute the negative sign, minus 2/3, and then it's going to be a plus 1 there. Okay. I've given up. I'm going to go ahead and throw the calculator in. Okay. So pi, maybe I don't want to put the pi in yet. 1/5 minus 2/3 plus 1 plus 1/5 minus 2/3 plus a 1. I'm getting 16 over 15. So pi times 16 over 15 then, which that can't be simplified any further. We're just going to call that 16 pi over 15. And that is our volume. Okay, if you really wanted to know what that volume was as a number, we could always do our answer times the pi. And it's like 3.35 cubic units to get that volume. Okay, but we tend to want those exact values for our integration end results. So again, the algebra part here is probably the most exhausting thing, but setting up the integral and then knocking down all that algebra, that's pretty much the game there. Okay. So does anybody have any questions about that problem? How are we feeling about that? It's a lot. It's where did the second pi go is what Ryan is asking. Um, Again, this requires like a dexterity with college algebra, right? So like the basic algebra I was saying is like, okay, if I have a pi here and a pi there, I'm factoring out the common factor of pi. So this was a common factor that I factored out just to make the algebra a little bit simpler for me. I could have also done something where I called this like, 1/5 and 1/5 makes 2/5. -2/3 and -2/3 makes -4/3, but I didn't want to maybe confuse you guys with a little bit of the algebra. Sometimes when I'm feeling too lazy, and maybe my lazy is different than y'all's lazy, my lazy is like I'm too lazy to pick up the calculator. And just because I have the dexterity of like, oh, I can see these guys have a common factor of pi, I'm just going to pull that out so I can do a little bit less multiplication, right? So that's what I did there. Or sometimes I'll say, oh, okay, can I combine any like terms here with the fractions? Because the fractions had different denominators, I was like, you know what, I'm just going to leave it as it lies. But those are just the algebra tricks that kind of make simplifying a little bit easier. I'm sure that, like, let's think for a moment. Back when you guys took Calculus 1, one of the hardest things, I think, in Calculus 1 is like when you start getting like the product rule and then the quotient rule. Do you guys remember how long those quotient rule problems were? And it required a lot of like, okay, let's factor something out and then try to cancel a factor with the denominator. Those skills are useful, but not every problem is going to be, are those skills going to be necessary, right? So for me, I know that for Ryan, this is probably a longer question, but This was just factoring out that common factor of pi just because it would help me do some of the math a little bit easier. Both of them had a pi, and so I can factor out the pi, leaving my final answer just with one pi. But this, as I've said before, this is a marathon, right? And you have to build up the endurance somehow. And in class, these things are going to drag on and on and on. And maybe I'm just dragging you along through these problems, and that's fine. That is how these courses go. Okay. But the real growth, the real learning is going to take place when you guys are going through those 10 to 15 problems in the homework. You're struggling a little bit. Don't ever take more than 30 minutes on a single problem. If you get stuck for after 10, 15 minutes of trying to work the problem out and you just like not getting the right answer, that's what Math World is there for, right? It is not throwing in the towel, it is being considerate of your own time, right? And your own I don't know, like energy, the desire to do these problems, right? You got to be able to say to yourself, okay, let me just ask somebody, am I on the right track? And at least that reassurance will sort of motivate you to keep going down the path that you've chosen, right? Because these are long, okay, and there's no getting away from that. The problems are going to stay long. They're going to get longer. Okay, so no comfort can be given there. We just need to get a lot more practice and take some breaks when we can. Okay. But that's why you also need to ask questions in class when I give you guys the space to do so. You know, great questions, great conversation coming out of this. Let's look at another example. Um, the washer method. Okay. We're going to get into another example, but after I kind of talk about this method first. Now, I already like was kind of misspeaking and calling these discs that we were making washers, because I knew that's where we were heading. Um, But the washer method can be based on this really simple analogy. Okay, so I'll give you guys a moment to sort of write this down, and then I'll jump into the explanation. Okay. Okay. So here's going to be the commentary for this. It's a really simple analogy. A washer is very much like a disc that has a hole cut out of it. So where we're going is that if we needed to find the area for just like a two-dimensional washer, think of that shape as having a larger circle with a smaller circle cut out, right? So with some basic geometry and a little bit of critical thinking or maybe a little bit of common sense, we can think about this diagram here having a larger radius and a smaller radius for this circular hole that we're cutting out of the washer. So think of that like we have a large circle and we're subtracting the area of this smaller inner circle. And that's how we're going to get the washer shape. Okay. So in terms of two-dimensional area, that's just going to be the area of the washer is equal to pi r squared, where I'm using capital R to indicate the larger radius for that larger circle, minus pi r squared, where I'm using lowercase r to indicate the area of the smaller radius for that smaller circle. Okay. Then similar to what we saw in the last problem, I have these two terms that are being subtracted from one another, but they both have a factor of pi. So I'm factoring out the pi here to make this, equivalent formula where we can just say that the total area of this washer is pi times the radius of the outer circle squared minus the radius of the inner circle squared. Again, the capital letter R means the outer radius or the larger radius, and the lowercase r means the smaller radius or the inner radius. Okay. So we're not working in two dimensions here, right? We're talking about volume. And so we can use this idea as a simplified analogy to find the volume of a solid formed by revolving the area of a region between two curves, two functions, around some axis where there's a hole formed in the middle. Okay. So that's where we're going in this next example. Okay. I'm going to give you guys a little bit more time to write this down. Okay, so let's look at that first example of the washer method. Um, but this is the image that you want to think about. Like we're going to have some axis of revolution here. We're going to be revolving a shape around there. So think about that shape as being a little rectangle that's floating above that axis. So that little shape has some outer radius. So think of this part here as being made up by the outer function. And this part down here as being the radius or the distance to the inner function. That's why these pictures are so important, so that we can see that we're going to get something that looks like this. This was my first attempt at drawing one of these things, but you can see that we have a hole here. So this is hollow. That little circular hollow area here, maybe I'll shade it in all the way. Not making the picture look any better here. But what you should be imagining is this shape, right? Like a tire shape with the hole cut out of the middle. Okay. The volume of this can be computed by using pi times the integral from a to b, so we'll have to know what those limits of integration are. And then the outer function, right, its radius squared minus the radius of the inner function squared, right? Again, that's just a direct analogy to that area that we saw on the previous page of notes. Okay, so the most important thing to do here is write down this formula. Okay. I'm going to go to the next example, which I haven't written down, so this will give you guys a chance to write it down as well. We're going to find the volume of the solid formed by revolving the region bounded by the graphs of y equals the square root of x and y equals x squared about the x-axis. Okay. Let me sort of fold this back so that it's not sort of flaring out at the sides. There we go. A little bit flatter. So what do you think the first step is going to be in solving a problem like this? Draw it. Draw it, right? We want to draw a sketch of this thing. Okay. So step one is going to be to draw the figure, the image, draw your sketch. Okay. So let's look at these two functions. I'm just going to put my x-axis here. And I mean, like to know what the limits of integration are, we really need to know what the intersection points of these functions are, because like on one of the previous examples that we did, I started my drawing and I was like, oh, it looks like this image actually extends into the negative region of the x-axis. So like we need to make sure that that's not happening. So finding those intersections of the functions uh, can be helpful, the intersections and endpoints. So we can find the intersections by setting these two functions equal to each other. Square root of x is equal to x squared, and then solving that. But this even though we have an x squared here, the radical part of this equation is probably the hardest part to deal with. So in order to cancel out a square root, I'm going to square both sides. Okay, so the square root will cancel the square. We have x is equal to x to the fourth power. And this is not looking any better here, but if I subtract the x to move it over here to the other side of the equation, I'll get 0 equals x to the fourth power minus x. And then whenever you have a polynomial, so a bunch of x's with a bunch of different exponents, we want to go ahead and factor out the common factor. Their common factor is just going to be an x. So we have x to the third minus 1 there. Okay. And those both equal 0. So if we're trying to solve this and we factored it, there's something called the zero product property, which says if I set x equal to 0, that's going to be one solution there. And if I set this equal to 0 and solve it, x to the third minus 1 equals 0. I'll find the other set of solutions. Adding the 1 over to the other side, x to the third equals positive 1. And then if I take the cube root of both sides, then I'll get x is equal to positive 1 there. So these are the intersection points. Okay. Those x values are really the only x values that we're concerned about. Okay. So 0 to 1 is what we're concerned about. And then the intersection points, you can plug them into either of these functions. I think that the square root probably will be the easiest function to find where these points of intersection are happening. If I plug in 0 here, then I'll get a y value of 0. So that means that they intersect here at 0, 0. And if I plug a 1 into that function, then they are intersecting at 1, 1. So that's 1, 1. If you vaguely remember what a square root function looks like, that looks like this kind of arc shape. So since I used red to indicate this, I'll say this arcs up like so. Okay. And then if you remember what kind of function this is a quadratic function, and that's going to look something like a U-shaped function. So if we're just looking on the sort of quadrant 1 here, then this will look something like this. And now this area here between these two curves kind of looks like maybe like a flower petal or like a leaf. Okay. Okay. And we want to think about like, okay, well, what are the radii that we need for this problem? Because remember, we're trying to get this guy revolved around the x-axis. That's our axis of revolution. So we're revolving this around here. So like, what would this shape look like if we revolved it? So imagine what the shape will look like. Well, if we have our axis of revolution here, and we have a shape that looks kind of like this, then when we revolve it around that axis, you'll get another shape that looks kind of like reflected below that axis, like so. And so we're going to have kind of an inner radius here for this circle. And it's kind of lopsided, but that's okay. This distance from here to here is going to be that inner radius. And the distance from here to here, right? Think of this like an outer circle. This distance here represents the outer radius. Okay, and let me maybe zoom in. So what we're really going to be looking at is kind of like this flower cup, or like a tulip-shaped circular region that has this kind of like vortex shape that's like carved out of it. Okay. Or maybe like a bowl with this kind of tornado shape that's carved out of it. Okay. Kind of hard to imagine, but really we need to think about, okay, well, which is the figure that determines the outer radius? The outer radius extends from the x-axis to which one of our functions? What's the function out here on the outside of our image? It's the square root function, right? So that tells us that y equals the square root of x. That's the outer function. And that means that this y equals x squared, that's going to be the inner function. Okay. So the inner radius, lowercase r, so capital R is going to be, and maybe to keep in line with this drawing, this coloration that I had here, I think I flip-flopped the colors so the colors don't matter. The square root of x, and the inner radius is made by x squared. Okay. So like putting this into that volume formula that we had, volume is going to be equal to pi times the integral from a to b. And then we needed the r of x squared, or that outer radius function, minus the r of x squared for that inner radius, and then all of that dx. Any questions before we start doing the integration part? Okay, well, let's start. So the volume is going to be integrated from 0 to 1, since if we look at our image, we're just going from 0 to 1 on the x-axis. Okay. We have a pi out here that I was forgetting. Okay, so pi times the integral from 0 to 1. And then we have the outer function. We said that that one was going to be the square root of x, right? So that's the square root of x, but we need to square that minus the inner function, which we said was going to be the x squared part, but we need to square that also, dx. Okay. So that's going to be pi integrated from 0 to 1. And then at least inside of the brackets here, the square root of x squared, that's just going to be an x, minus x to the fourth dx. And thankfully, again, the calculus is the easy part of this. Thankfully, this is a nice looking polynomial function, so we can take the integral pretty straightforward, or in a pretty straightforward manner. That will just be pi times, what do we have here? 1/2 x squared minus, this is going to be 1/5 x to the fifth power. And then just evaluate that from 0 to 1. Does that feel okay? Not too bad, right? It's really all the prep work that's required for these problems to sort of build those skills. Okay. Um, then we can evaluate this like we always do. So we can go ahead and do pi times 1/2 times 1 squared minus 1/5 times 1 to the 5th minus pi, and that's going to be 1/2 times 0 squared minus 1/5 times 0 to the 5th. And the nice thing about this integral is that this guy over here is just 0, right? Okay, so if this is just pi times 0, then since all of this collapses to just being 0, then that means we can sort of ignore that part of the integral. All we're really focusing on is this pi times 1/2 times 1 is just going to be 1/2 minus 1/5. Again, if you don't feel like going back to your grade school arithmetic and subtracting fractions, that's perfectly fine. The arithmetic stuff can be done in the calculator. I have no issue with that, just as long as you show some of these intermediate steps. So this is just going to be what? 1/2 minus 1/5, which would be what? So 5/10 minus 2/10, 3/10 pi times 3/10, which is just equal to 3 pi over 10. And that's the volume of that pretty interesting shape that we found. Okay. Now, I'm going to go ahead and end the recording and our discussion of these integrals to like there. But I do want to let you guys know that there is a fourth example here that they have in the textbook, and you guys are going to encounter in the homework if you haven't already, where they start integrating with respect to y. And there was a similar problem in section 7.1. So before I let you guys go, I do want to sort of show you guys in Canvas that I worked an additional problem for you guys to review on your own. So in Module 2, if you look at the Module 2 in-class notes, I haven't made a video for this, but I did put some bonus notes here that say integrating the area with respect to y. So if we look at those notes, I took an extra example out of section 7.1, and I worked through that problem. Those problems were given as x equals 3 minus y squared, so that's a function of y, and x equals y plus 1, again, another function of y. So they're integrating with respect to y, which means that the drawing that you end up getting looks something like this. If you review those notes, you see that we have kind of a rectangle here that's sort of laid down on its side because it's going width-wise, it's going with respect to the x-axis, but the thickness of that rectangle or the width of the rectangle is going up and down, so that's going to be delta y or dy, right? So I did work out this example and put those that extra problem of notes here. But what I'm going to do, just so you guys have like more interactive set of notes, is later today in the lecture videos for the disc method here, I'm going to put not only this class video, but I will put an extra video in there where I work through the problem where we're integrating that volume with respect to y, just so you guys have some practice or an additional source to like look at. If that doesn't come fast enough for you guys to work on these homework problems, then like there's a vast repository of similar examples that you guys can find on YouTube or Khan Academy. But I will later today record this video where I'm going through a fourth example so that you guys have that, because sometimes it is also kind of overwhelming to search for these videos on your own. So I will put this extra video. So there's going to be 2 little videos here under 7.2 disc method later. Okay. Does that make sense? Does anybody have any questions? How are we feeling? Okay. Kind of a lot for a Monday morning. I totally get it. I'm sure that some of you guys are still very much focused on getting test one completed. Remember that you have 3 attempts to do that. And so, if you took your first or your second attempt already, you should be able to view the problems that you've already worked out so that you can see which ones you got incorrect. I think the settings in Canvas say it'll show you the ones that you did incorrectly so that you can correct them for your second or third attempt. But I think that it's very generous that I'm giving you guys 3 attempts on these tests, and your highest score is going to be the one that's recorded. So just make sure you compile all that work together, and when you're done with all of the attempts that you're going to make, that you submit your handwritten work for those corrected problems or the ones that are nice and clean, that you submit that to Canvas because otherwise you're going to get a 0 on the test if I don't see the handwritten work. Okay. Um, but that's all I have for you guys today. So if you have any questions later, just shoot me a message in Canvas. Drop by Math World to ask some of the tutors for help. Um, and yeah, we'll go from there. I'll see you guys on Wednesday.